Yes, now we will give this theorem. This theorem, it is important, and sometimes by using this theorem, it is easy to see that L is 1-to-1. It's okay if we know that the kernel L is a linear transformation, and one linear transformation, a linear transformation is 1-to-1 if and only if kernel L is 0 only. It's okay, zero set, and means contains only any zero vector, not contain non-zero vector. It's okay. We know kernel, and look at the kernel. There exists non-zero vector in kernel L or not. If there exists non-zero vector in kernel L, L is not 1-to-1. Otherwise, L is 1-to-1. It's okay. So, and how to show that? It is easy to see that. Use and first of all, let's prove that these direction and means and they take the one-to-one linear map. Our aim is to show that kernel L this set not contain the non-zero vector. It's okay. Assume that L is 1-to-1 and take the arbitrary vector in kernel L. It's okay. So and the V in kernel L and means and use the definition of the kernel, and L of V should be 0. L of V is 0, and also we know that L is linear transformation. If our map is the linear transformation, we know that always 0, L of 0 is 0. So L of V is 0, L of 0 is 0, so means L of V is equal L of 0. But we know that L is the 1-to-1 assumption. From assumption, L is 1-to-1. So we obtain, and the V is 0 because L is 1-to-1. V should be 0. It's okay. So and arbitrary vector in kernel, and this V is 0. So means and the kernel L is this set. It's okay. No non-zero vector in kernel L. So now let's prove the other direction. This direction is okay. Assume the kernel L is this set. Our aim is to show that kernel L is 1-to-1 or not. It's okay. So suppose that kernel L this set, and our aim is to show that L is 1-to-1. How to show that? And take the same images. L of U is equal L of V. Our aim is to show that U is equal V or not. It's okay. So, and what does it mean that this one? L of U minus L of V is 0. It's okay. So L is the linear transformation. So, and the left side is equal L of U minus V is 0. So image is 0, and we know that this one is in kernel, because the kernel contains vectors such that image should be 0. Yes, and so U minus V is kernel. We know that at the beginning, and kernel at 0 is okay, and then U minus V is 0, and we obtain U is equal V, and L is a linear map. It's okay. L is L is 1-to-1 linear map. It's okay. So, and now let's give the definition of the range. What's the range? And the L is a linear transformation from V to W, linear transformation. The range of L is the set such that this set contains vector W such that, and for example here, W, this W in, and the sun is in, and the range L, if there exists one vector here V such that L of V is equal W. It's okay, W. And the pre-image should be on the V here. It's okay if there exists an V such that L of V is W, so W in range of L. It's okay. This one is, and we know that, and the kernel is here, for example, and the images 0, and also we know that, and 0 here. because L is a transformation and is 0 here, L of 0, 0, and this one. This one is range of L. This one is if, and here vector goes to 0, it's okay, maps to 0, and then this one is kernel, and this one is range of L. It's okay. This one. So, and here range of L is equal W. It's okay. All and the space here, range of L. So then L is 1 to 1. L is 1 to 1. Another fact, if L is a linear transformation, then range of L not only set, this one is a subspace of W. It's okay. This one is important and the fact. And also, other and the fact, we know that kernel L here, kernel L is a subspace. Kernel L is a subspace of V, and the image range of L is a subspace of W. So natural question, what can you say about the dimension of L and range of L, and what's the relation and the between and the kernel L and range of L? Because we have two subspace, kernel and range, and the kernel is a subspace of V, image range of L is a subspace of W. So what's the relation and the between and the dimension? It's okay, dimension. And another fact, it is important fact, dimension of kernel L plus dimension of range is equal dimension of V. It's okay. Let's give an example to understand these relations. It's okay. Take this map from R cube to R cube, and take the vector a sub 1, a sub 2, a sub 3, and the image of this vector, this one. First component plus the last component, first plus second component, the last component should be second component minus last component. So question here, what's the dimension of kernel L? What's the dimension of range of L? And define the dimension of kernel and the range. And also, it's okay. So dimension means you have to check that, and the basis is okay. You have to find the basis, and then the number of factors in basis, and it gives the dimension. And first of all, you have to find the basis for kernel L, and then write the dimension. It's okay, kernel L. So kernel, and let's find the kernel L. It's okay. How to find the kernel L? And they take the arbitrary vector here. Our aim is to, first of all, what's the basis for kernel L? It's okay, kernel L. And then write the dimension. And they take the arbitrary vector in kernel. And so what does it mean? And we know that and the kernel contains and the vector such that image of these vectors should be 0. It's okay. So, and what's the use of this one? L of and the vector image of and this vector is this one, but is in kernel and means this one should be 0 vector. So, and this vector is equal this one and means first component should be first component, second one, and the last one 0 should be. So we obtain the system. It's okay. So, and this one and it gives one linear system. So, and it solved this system, and then and here let's find the basis for the solution space. It's okay, of the homogeneous system. This one is the homogeneous system. It's okay, write the solution. Our aim solve this one, and the first, and this one gives the solutions. It's okay, solutions, and write the solution space. It's okay, and solution space gives the elements of and the kernel. So, and the solution space is here kernel, and our aim is to find the basis and means basis for solution space. It's okay. Let's give this remark. It is important, and take the L is a linear transformation defined by this one. L of x is equal A times x. A is m by n matrix. It's okay, m by n matrix. then kernel of L is the solution space of the homogeneous system. It's okay. So here, and this one kernel, and it is easy to see that kernel L, take the arbitrary and the vector in kernel L, so we obtain homogeneous system. Our aim is to find these and the vectors. So, and find the A sub 1, A sub 2, A sub 3. And this one gives the solution space. Our aim is to catch the solution space. And then solution space is a kernel. Our aim is to find the basis for kernel and means find basis for the solution space. It's okay. So how to solve then this one? Write the augmented matrix. We know and how to solve any homogeneous and system. It's okay, homogeneous system. And then write the augmented matrix, apply the operation, we get the reduced row echelon form, write the solution. Solution here, and the last entry A sub 3 is the free variable R, and take the R, any real number, we obtain and the minus R, and this one. So R arbitrary real number, so we obtain infinitely many solutions. It's okay. So solution set right here minus R. This one can be written minus 1 R. This one is the solution set. And we know that solution set is a solution space from the previous lecture. This one also solution space. It's okay. And here we know that and these and the system, homogeneous system coming from kernel. And these vector in kernel. So means this one is the solution set, solution space, also kernel L. So our aim is to find the dimension. So means and look at this space, solution space, find the basis. How to find? Look at the rewrite and this vector. So this one gives the basis. Every vector here generate by using the minus 1. It's okay. So and this one is a basis, and the kernel is a subspace. Kernel L contains infinitely many vectors, but basis contains only one vector. It's okay. This one is this vector minus 1. If we know when this vector, it is possible to generate the all vectors. It's okay. So what is the dimension of kernel? And the number of vectors in this set and this space is 1. It's okay. So dimension of kernel is 1. It's okay. Any question? This one, it is important and the problem because and this one contains solution of the homogeneous system, and we know how to solve any homogeneous system, and also write the solution set. We know solution set, solution space. It's okay. And how to find basis. This one gives the method, and if we obtain this and this space, how to find basis, we'll rewrite, and then we obtain basis. It's okay. So dimension is 1. So use the previous and the theorem. What's the theorem? And this theorem, this fact. Dimension of kernel is plus dimension of range is equal dimension of V. And here our question, let's come back our question. Our aim is to find kernel. Yes, we know, and this one is 1. And the next question, find the dimension of range of L. So use this fact. This one is 1. Dimension of V here, yes, are cube, and the dimension 3. This one is 3. So what's this one? This one is 2. It's okay. Dimension of range of L is 2. Dimension is 2. But here, be careful. And if we know that this fact, it is easy to see that. And now, and also, let's find find the range of L and for basis. It's okay. Let's check that this one is true or not. How to check that? And write the Basis for and the, what's the basis? Basis for range of L. It's okay here. What is the range? Range is here, and let's here, and take the arbitrary vector a sub 1, a sub 2, a sub 3, and image of and this one a sub 1 plus a sub 2, and look at this rule L. L is this one here. L is this one. L of V is this one. It's okay. So look at this one. Range of L. A sub 1 plus a sub 3, a sub 2, a sub 2 minus a sub 3. This one. This one is in range of L. It's okay. Range of L. This one is R cube. R cube. It's okay. This one. So, and our aim is to find the basis for and range of L. It's okay. And so means every vector in range of L is generated by using the basis. So, and this one is L of V, and here it's okay. This one. Our aim is to get the basis. Basis this one. It's okay for the range of L. How to find? Yes, and look at the images, and every vector here in range of L is in this form. It's okay, and every vector. Sorry. Every vector in range of L is of this form. What's the form? A sub 1 plus a sub 3, a sub 2 plus a sub 1 plus a sub 2, sorry, a sub 2 minus a sub 3. It's okay, this one. So, and our aim is to find the basis. So, and our aim is to generate these vectors. How to generate these vector? And this vector, this one, is okay. This one is W, for example. W is can be written as, our aim is to find the vectors such that and these vectors generates the and the W. It's okay. So, and we can write this one is rewrite. So this one is equal, yes, a sub 1. Look at the a sub 1. The coefficient of a sub 1, 1, 1, 0. And multiply a sub 1 plus contains a sub 2. Write the coefficient of a sub 2 and 0, 1, 1. So a sub 2 plus coefficient of a sub 3, 1, 0, minus 1. 1, 0, minus 1, multiply a sub 3. Yes, and this vector in range of L here, it's okay. This one is and the arbitrary vector in range of L. So every vector can be written in this form. And look at this one, how to write. For example, look at the coefficient of a sub 1, 1, 1, 0. It's okay, plus. Because no 0 and this one is open. Look at the a sub 2, there is no a sub 2. And here, this one, it's okay. And 0, 0, 1, 1. It's okay. And then we obtain under this form. So means, and every vector in range of L here can be generated and using the and this one W1, W2, W3, and okay, this one W1, W2, W3, and yes, we obtain under this set. It's okay. Using this set 110 and 011, and also 1 0 minus 1, and it generates range of L. Our aim is to find the basis, and also basis to be basis, and it is said to be basis should be linearly independent. It's okay. This one is a set linearly independent, but this one is linearly independent, not linearly independent. Look at this one. Take, for example, take this one, W1. This one is W2, this one is W3. W1 minus W2 is equal W3. So, and we can ignore W3 because it is possible to generate W3 and by using the W1, W2. So, eliminate the W3, 1 1 0, 0 1 1, linearly independent set. Independent. So this one is a basis. This one is a basis for range of L. So what's the dimension? Dimension of range of L is the number of we know under this notation number of the vectors in B. It's okay, not determinant. If B is a matrix, this one is the determinant, but B is a set, this one is the number of vectors in B. This one is 2. It's okay, dimension is 2. Let's come back. Our aim is to check that this dimension 2. It's okay, yes. Any question? And also find, and we have got the basis for range of L. Any question? No question. Okay. That's one more example. It's okay. And find a basis for solution space AX is 0. And this one. We know that this fact. Look at this fact. This fact is important. And this one remark. It's okay. L is a linear transformation from R to N and from Rn to Rm is a linear transformation, but L of x A times x. It's okay. And sometimes yes, using the matrix A, and we obtain the linear transformation. If we got the L linear transformation is L of x is A times x, and the kernel of L is the solution space of the homogeneous system. And this one is homework. It's okay. This one, find the solution space if R and the map from R to the 4, and this one is R to the 4. It's okay. And this one is, and the L of V, and the L of V is A times and or X. It's okay. This one AX. It's okay. So, and the solution, find the solution space. And what's the solution space here? And find the basis, and this one is a basis of kernel L. It's okay. So here construct the system AX0 homogeneous system. And so solve this system. How to solve? Write the augmented matrix. Write the L 1 2 minus 2 0 1 3 1 minus 2 2 6 2 minus 4 1 minus 1 minus 2 2 0 0 0 0, and write the augmented matrix. And then we obtain this one. For example, 1 0 0 minus 1 0 1 2 0 0 0 0 0 0 0. It's okay, this one. So we obtain the solution, and x1 is is equal x4, x2 is minus 2, x3, x3 free is okay, and x4 free variable. This one is a real number, another real number s is okay. We get infinitely many solution, and the solution set is yes x1, x2, x3, x4. This one is the solution set, solution space is equal, yes, for example, R and S, x1 is S, x2 is 2R, R, S. And rewrite this one. It is important because to see that and the basis for this space is okay. The coefficient of R, 0, 2, 1, 0, plus coefficient of S, 1, 0, 0, 1 times S, such that R and S real numbers. It's okay. So this one is solution space, and solution space of AX is 0 or null space. And also we know that this one is kernel. Also this one is kernel of L. It's okay. So basis, look at this one, gives the basis. Basis is yes 0, 2, 1, 0 and 1, 0, 0, 1, and spans and kernel L and or S. It's okay. Depends on you. It's okay. S, span S. But our aim is to see that this one is a basis and check that, and the homework B is also linearly independent. Homework, this one. So B is a basis for S solution space and also kernel. It's okay. What's the dimension? Dimension of kernel L is 2 because contains 2 vectors. It's okay. Any question here? No question? Okay. And also, and here, this one, and if, let's come back, but, and if L is a, can be, and L is the x, any vector, L of x is AX, A times x, this one is called and the standard, and let's come back here, not this one. This one is called the standard matrix representing L. It's okay, this one. If L is Rn, Rm is a linear transformation. A sub 1, A sub 2, A sub n, the natural basis is okay. Natural basis for Rn is okay. A is the M and N matrix, and such that columns, J columns, the image of the vector J is okay. And so L can be written in this form. L of x is the AX, and means image of x can be written and by using the matrix A. And this matrix is unique. It's okay. This matrix is called standard matrix representing L. It's okay. And so, and means here, and the linear transformation, and every linear transformation and can be written in this form, and we obtain, and the A is here is the standard matrix. It's okay, representing L. Let's give an example to understand and this one. For example, and the L is from R cube to R square. The linear transformation defined by this one. It's okay. So find the standard matrix representing L. So, and look at write and the standard and the basis for our cube: a sub 1, a sub 2, a sub 3, 1 0 0 0 1 0 0 0 1. We know and this one, these and the basis for and our cube. It's okay. So, and how to find L of x is AX. Our aim is to find the matrix A for and these L, these math. And how to find, and A is the matrix. Look at the first column, L of E1, the image of first and the vector in basis. And the second column, image of second vector, and the last column, image of third vector, A. So, and L100 and this one. What is the formula? And this one for L, this one. And substitute here. It's okay. X1 is 1, X2 is 0, 1, 0, 0, 0. So we obtain plus and minus, so 1, 0. It's okay. 1 0, and substitute and the second vector in basis 0 1 0, and use and the same formula 2 3, and then the next one, this one. So A is L of E1, this one, L of E2, and L of E3. This one is the matrix for L. It's okay. Any question? Okay. No question? And then let's stop here. It's okay.